All right, here's an example using the squeeze theorem. So the idea behind that is we need to find two functions um, that would squeeze this function posed here, the theta squared cosine 1 over theta, in order to evaluate that limit. Because we can see right off the bat here, right, that I can't just use direct substitution. The first part is great, plug in 0 into theta, theta squared, 0 squared is 0. But right here, direct substitution, we cannot take cosine of 1 over 0. All right. Now, sometimes these get complex and picking functions is weird. Really explaining this idea is kind of strange, but this one isn't terrible. Most of them, the idea is this, that cosine of any angle, right? If I were to think of the graph of cosine, it ranges from -1 to 1. So I know that this value will yield something in there, and it includes -1 to 1, right? And theta squared, so when I substitute values in with that theta squared, as I'm approaching 0, let's really only concentrate like, I don't know, from -1 to 1 as well, just for simplicity, but it really wouldn't matter. I'm multiplying some value in between -1 to 1 with this theta squared, right? So think about it. If we're approaching 0, if I'm choosing values in that interval, it's going to just create these to be less than -1 to 1. Oftentimes you want to pull up a graph to help you see this, and the directions for this problem in the book also say that. Find a f of x, g of x, and h of x to use. So what we're trying to do is find some f of x that will always be less than or equal to cosine, the entire function there, theta squared cosine 1 over theta, and so we're calling this one g of x and h of x. Okay, I want to find two functions that would contain that. It happens that in this example, really just using negative theta squared and theta squared, and oftentimes that is the case, this here will bound this trig function, because remember all trig functions, so cosine does start up here, but it doesn't matter. They're periodic from -1 to 1 is the range. So what this theta squared does, we'll look at that in a graph that I had pulled up. Oops. So in GeoGebra, I went ahead and graphed theta squared cosine 1 over theta, and then negative theta squared, and then positive theta squared. And you can see that with FG and H, not the same FG and H. I should have done it the same as what I just labeled them, but that's okay. The middle one is the theta squared cosine 1 over theta. And notice it's contained within that negative theta squared and theta squared. No matter how close I zoom in, it squeezes it right to that 0 there. Now, that wasn't just luck by chance or anything. In trig, you had it learned actually some properties that what happens when you adjust cosine and how to graph that and what happens. So here's this example, and you can see, right, if I zoom out, it's contained the entire time, but it doesn't really matter. I'd need to look at as we're approaching 0 anyways. So let's go back here. So what the squeeze theorem says then is if I can take the limit as theta goes to 0, right, that was the original question, limit as theta goes to 0, of this f of x, so of negative theta squared, and the limit of as theta approaches 0 of this right side, h of x, theta squared, if those can be found, and because g of x, the original problem, is contained within both of those functions, I know that the limit would be equal to the left and the right. So I could use direct substitution. Negative 0 squared is 0, and 0 squared is 0. And since those two limits, the limit as theta goes 0 of f of x and h of x is 0, by the squeeze theorem, the inner limit also has to be 0, right? I squeezed it down as we approached 0 from the left of f of x. So below, right, we're squeezing it from below. It approached 0, and from above, it approached 0. And so therefore, the overall limit of the original problem is in fact 0 by the squeeze theorem.